Okay, so I'm just going to give a really brief intro of stock recruit relationships and then talk about how they can be used to predict or forecast salmon returns. It seems like there's sort of a variety of backgrounds, so I'll start really basic, but I won't spend too much time about it. Happy to talk more. Stock recruit relationships are just the relationship between spawning stock size, so this is usually egg count or spawner number, and the resulting recruits. So since we're talking about salmon here, it's super simple because they're semiparous, so they return, when they return to the rivers, that's what we consider recruits. That plus escapement plus catch, pretty much all the returning salmon. And I guess I'll just say that this is a really important relationship for managing fisheries in general, but certainly for managing salmon because of their life history characteristics. And so again, it's that relationship between the spawning population size on the x-axis and the resulting recruits. And a lot of times they look like this. So sort of shotgun scatter, but you can see some emerging patterns, which is that at low stock sizes, there's lower recruitments, and at higher, there's generally higher, but it seems to have hit like some sort of upper limit. Again, this might be really elementary to some of you, but I think it's good to just go over the basics. And so if we assumed that there was density independent, or that stock size or recruits just increased as stock size increased with no bound, we would see sort of a linear proportional relationship between stock size and recruits. But in reality, we actually know that there are ecological mechanisms that sort of limit recruitment at higher stock size. So this could be competition. With salmon, we're thinking about, here, I'll just go to the next. So this is what we call compensation. And so again, that density independent relationship is just a linear relationship. We think about things like competition or limited habitat, we would start to see a leveling off of the recruitment at high stock size. So think salmon in a river, there's only so many that can spawn in that river. And then overcompensation happens when at really high stock sizes, we actually see reduced recruitment. And this happens when things like cannibalism, so they're like actually eating juvenile fish, so there's like lower recruits. Or with salmon, it can happen when salmon, you know, they'll dig the nest to lay the eggs, but then a female will come, another female will come and dig up those eggs and lay her own eggs. So it's sort of like this negative effect of more spawners. And traditionally there are, so we know that there's these relationships that we kind of see in the empirical data between spawners and recruits, but how do we model that? So there's been a bunch of models, way more than just these two, but these are sort of the classic ones that I'm sure everyone has heard the names of, the Beverton-Holt and the Ricker model. And I mean, I just kind of explained them in the slide before, but the Beverton-Holt model sort of increases to a point, and then the recruit production tapers off at a low, at high stock sizes. And the Ricker model is more capturing that overcompensation. So we see reduced productivity or reduced recruitment at high stock sizes. And a lot of times the Ricker is used for salmon, but you can use both, and it really is going to be driven by the data that you have for that given stock or species. And so people like to think of the Ricker as like the classic salmon stock recruit model, but sometimes the Beverton-Holt fits better. Sometimes you don't see that overcompensation happening. And then, so in terms of using these seemingly simple relationships between stock and recruitment to forecast or to predict runs in the future, we're fitting them with two, as you saw in the previous slide, two parameters. So there's the Ricker A parameter in both of these, in both the Beverton-Holt and the Ricker model. Sorry, I should say the alpha or the A parameter. I always call it the Ricker A because I use the Ricker, but which sort of has to do with the productivity or the slope of these curves at low stock sizes. So this is going to be a less productive stock because it has a slower slope, whereas this is a really productive stock. So at low stock sizes, it's producing a lot of recruits really quickly. So that's the Ricker A the A parameter or alpha parameter of the stock recruit model. And then the B has to do with this part of the curve, which is sort of the capacity parameter or the density dependence parameter. And it controls basically what's the upper limit of the capacity that a stock can have. And so you can see this one actually is with different, a lot of these figures come from the classic Carl Walters and Ray Hilborn textbook on stock assessment. But you can see this is with different, so this is like fitting Ricker curves with different A values, and it changes again the slope of the curve at low stock sizes. And stop me if anyone has questions. I think it might be just easier to do it that way. So I'm just going to touch on this. But it's not really what the focus of the workshop is about. From this simple relationship, you can derive management quantities. So you can derive maximum sustainable yield, spawners at maximum sustainable yield, recruits at maximum sustainable yield. So this relationship between spawners and resulting recruits is really powerful for managing fish stocks. But that's all I'm going to say on that, because it doesn't really have to do with what we're getting at here. So I'll introduce one more really valuable model, which is you can reparameterize both the Beverton Hall and the Ricker model. And the Ricker model is really easy because if you just take the log of both sides of the model, I should have had the original model up here. But if you just take the log of both sides of the Ricker model, you get a simple linear regression. And this turns into, now you're looking at log recruits per spawner. So that's sort of like the per capita recruitment. And it's related to these two parameters in spawning biomass or spawning number. And then the Ricker A parameter is just the intercept of a linear regression, and the B parameter is the slope. So it's super simple to model when you have a linear regression, because that's like one of the simplest models. So a lot of times it will be converted into this to look at, for instance, hold on, let's just see where we're going here. Yeah, so a lot of times this will be the form that they use to fit either fit a stock recruit model or to predict from it. So that's what we're going to talk about next. Yeah, so the first thing I have to say is that when we're using these models, we can fit them. So we have this empirical data, spawners and resulting recruitment, and we might be able to use them to forecast, but that's, remember, different from fitting. And Tanya kind of just went over this. You can fit the model, but then how can you use it to sort of predict? And for salmon, it's really nice because they're semiparous. So we know that if there's spawners in 1 year and we know that they all or mostly return at age 4, or we know when they return, then we can say, okay, how many returners will be from the spawners? It seems pretty simple. Like this simple relationship could, in theory, predict returners from spawners. But in reality, the relationship is really highly variable, not necessarily stationary through time, which it should really be in theory. And there may be other things influencing recruitment other than just spawning stock biomass, right? If that perfectly predicted, you would see the line fit perfectly. But in reality, we have like this, again, shotgun scatter relationship between spawners and recruits. And often it's a lot tighter at low stock sizes, but to get to those low stock sizes, you have to really fish the stock down, like near zero on the spawner recruit curve. So it's tough sometimes to know this exact curve. So it's helpful to think about the relationship between stock and recruitment actually as distributions of recruits for each spawning biomass, and the distributions get wider as the stock sizes get bigger. So bigger stock sizes can, depending on, again, environmental conditions and other things, produce variable recruits. That's really important because that's why it's important to have more models that don't just look at spawner abundance, but might incorporate some environmental drivers that might explain some of this variability at high stock sizes, or some way to like get at that uncertainty, which is like why a lot of people do use Bayesian models or models that are good, well equipped at handling uncertainty. There's other limitations besides, I just touched on the contrast in data. Like you really want to be able to pull this relationship out, you really want a lot of different spawning stock sizes over a lot of different years. So you need a lot of data to pull that relationship out. Luckily for salmon, we have a lot of data. So we do have like well-defined as you can relationships for these. There are other sort of limitations that I'm not going to talk about here, but certainly if you're using these stock recruit models, you might want to think harder about, and I'm happy to answer questions, but in the interest of time, how much more time do I have left? Sorry, I have not been keeping track.
I think you're good because we're just going to go into sort of a open session.
Okay,
now, so.
yeah, I'm almost done. So, okay, so I talked about fitting versus predicting. A lot of times these stock recruit relationships are used to look at, and this is what I'm doing for my PhD research, what has driven in the past, what has driven salmon productivity or survival. And this is, again, the linearized version of that Ricker stock recruit function. And because it's just a simple linear regression, you can throw in other covariates. You could throw in, it's just a multivariate regression then. So you could throw in sea surface temperature, for instance, and you could lag it to the wherever you're saying. So you come up with a hypothesis and say, oh, we think that high sea surface temperature on smolt out migration impacts salmon survival. And then you have this relationship between the recruits and spawner, and you can lag it to the year of the recruits that you might see them interacting with the sea surface temperature. So if the sockeye mature at age 4 and you think they run at age 1 or 2, you can lag it. So it's really, the linearized version is really useful for including covariates and modeling sort of what we've seen, what's contributing to the variability in that log recruits per spawner or productivity through time. But I also mentioned that these tend not to be stationary. So in theory, these relationships, because you're using a bunch of years of data to pull out this curve, should hold over time. We found that, or a lot of research has found that it's not necessarily stationary. So that makes it a little trickier to model as well. And that's when you'll see more time series models come into these simple linear Ricker models, even to say like, okay, the A parameter, which kind of represents productivity, what if we assumed that that's not stationary and we varied that over time with a random walk model or a time series model? This is like a little beyond the scope of my talk right now, but so people try to sort of get at the variability that way too. And again, it's getting back to the idea that we want to try to explain like what's happening. So we have this sort of mean average relationship when we fit these models, but we want to get at what's happening with all this variation, and that would help us forecast better and use it to predict as opposed to just describe, right? I think that's pretty much it, but I'm happy to like talk more and answer questions.
Yeah, that's awesome. Awesome, Haley.